office has been following his work for several years, and we are very happy to have him here today to tell us about it. So thank you very much.
Yeah, so thank you very much. It's really great to be here and to chat with all of you. So today my talk will be about moving towards large-scale natural language inference with distributional semantics. And so just at a very high level, the motivation of my work is the vast amounts of text that is now available. So suppose we look at the number of web pages that have been indexed by Google, and we look back a couple of years. Back in 1998, there were 26 million web pages indexed. And then fast forward 10 years, and this has become 1 trillion. And then if we look at last year, that has again increased very dramatically to 30 trillion web pages. And even within the span of the last year, this has doubled yet again to over 60 trillion web pages today. So with this large amounts of text data, what I'm interested in is how we can actually structure this data, as well as how we can understand this data to enable some interesting text applications. So what are some of these applications? So one of them is automatic summarization, the task of shortening some text while retaining the important information. And in the research community, there's been a lot of work in this area over the past 15, 20 years. So more recently, there's also been some commercial success. So for example, you might have heard of Sumly, which is this news text summarization company that got acquired by Yahoo. So another application is in this more focused collection of patient record data. So this is an ongoing project at an Ontario mental health hospital that I learned about. So here we have a collection of patient records for patients who are suffering from depression. And so the first thing you can do with this collection of data is to extract some useful information from it. So for example, you can extract some profile of the patient, such as their gender, age, or weight. You can extract the kinds of drugs they're taking, the efficacy of the drugs, as well as any side effects that these drugs might have. But then after doing this extraction, you can do more. You can then ask interesting questions of the data. So for example, you can ask which drug combinations are the most successful in treating depression, or how we can actually minimize the side effects of the drugs, or even interactions between patient attributes and these outcomes that we're interested in order to develop more effective or tailored drug therapy. So I'm going to argue that what makes these and other text applications so interesting and impressive is that they appear to require the automation of natural language inference. So what do I mean by natural language inference? Here are some examples. So the first is to understand paraphrases. And of course, there's a lot of work here on that. So it's important in many text applications to know that a patient who gained 10 pounds is the same as a patient who experienced a 10-pound weight gain. Another example is in determining redundant sentences. So in summarization, suppose we have a summarization system that has already decided to include the sentence, search crews determined the source of the fire which damaged 5 homes. So if that's the case, then there's no need to include the sentence, the fire wrecked 5 homes, because that's entailed from the first sentence. So a more general inference problem is that of checking the consistency of text. So the easiest way to explain this is to actually look at a passage that is inconsistent. So in this passage, we have police specializing in explosives diffused to rockets, some 100 people were working inside the plant, and 100 people were in Europe. So this is inconsistent because the rockets were diffused, and yet the people inside the plant were still diffused. So being able to automate this type of inference can have applications in, say, question answering or patent checking. So in question answering, you can reformulate your question in terms of some declarative statement and check to see if it's consistent with your body of knowledge. And in patent checking, you might want to check that all of the facts inside the patent that you're going to submit are internally consistent, so you can submit a valid patent and get rich. All right, so then this talk will be about moving towards automated inference over this kind of text. So we've seen some practical motivations to care about natural language inference. And this actually is situated within the background of logical semantics. So here, this is a tradition that goes back quite a bit, where we want to represent the meaning of natural language in terms of some formal logical representation. So most commonly, this is done using, say, first-order logic. So we have this sentence like, the patient took the pills, being represented by this logical formula. So from a theoretical perspective, we also care about inference, because actually inference is one of the key goals of semantics in the first place. So as Montague put it, the basic aim of semantics is to characterize the notion of a true sentence and of entailment. So one of the bottlenecks towards moving towards the automated inference is this requirement for domain knowledge. So when performing inference within a specific domain, we need to be able to know about the concepts in the domain, how these concepts are related to each other, as well as how they're expressed in text. So in the patient record domain that I discussed, you have concepts like the patient and its attributes, the drugs, the efficacy, the side effects, and so forth. So now suppose we're moving to an entirely new domain. Now we want to try to come up with strategies to prevent crime. So if that's the case, now we have an entirely new set of concepts like the criminal, the victim, and their attributes, the crime itself, or the location of the crime. So given that there are over 60 trillion web pages on who knows how many topics, it's not feasible to try to annotate all of this domain knowledge. So then we need to come up with some methods to automate this process. And the solution that I'll explore is to use the data itself to learn about the structure within the data. So it's true that raw text isn't structured, but this is only from the point of view of databases. As you're all aware, there's a lot of linguistic structure and regularities within text itself. And so I'll talk about using these linguistic regularities to learn domain structure. So just to be clear, this is a parse tree, but this is not going to be a parsing talk. Instead, I'll be examining how maybe this type of syntactic structure could actually help us learn the kind of semantic structures that I'm interested in. All right, and the kind of semantics that I'll discuss is that of distributional semantics, which is captured by the aphorism that you shall know a word by the company it keeps. So for example, the meaning of the word pill can be characterized by words that it tends to co-occur with, like administered, take, or often. So just very briefly, how you train this type of model is you end up with some vector representation of the meaning of the word. And you do this by training the vector by first extracting all of the occurrences of the target word pill within the corpus, as well as all of the context that pill appears in. And then you simply count up all of the content words, say within a context word. And to do so, you get some vector representation of the word pill. And what can you do with this? So the first thing you can do with this, the most traditional thing, is to have some notion of semantic relatedness by comparing the vectors themselves of the words. So for example, you can assert that the meanings of pill and medicine are similar because their vector representations are similar, according to, say, cosine similarity, so having a small angle between the vectors. On the other hand, unrelated words like pill and algebra are probably different, and so their vector representations are hopefully also different with a large angle or a low cosine similarity. But in order to move towards the type of inferences I was talking about earlier, you actually need to model more than word-level meaning. You also need to model phrase-level meaning, and so the meanings of arbitrary phrases and sentences, including ones that you've never seen before. So in other words, language is creative and compositional. So it's likely, unless you're some expert in animal trivia, it's likely the fact that you've never heard this particular sentence, a flamingo can only eat when its head is upside down. And yet we're all able to understand the meaning of this sentence because we know about the meanings of the parts and how they're put together to form the meaning of the whole sentence. And of course, there are exceptions to compositionality, so say idioms or other potential phenomena. But by and large, a large part of language can be described compositionally. So we want our semantic theory to also be compositional for these cases. So in distributional semantics, there's been a number of recent papers focusing on compositional distributional semantics. And this is operationalized by these vector composition operators. So some of these are actually very simple. So for example, suppose we're trying to model the meaning of the phrase to take a pill. So if that's the case, you have some vectors for the individual parts, take and pill, and you apply some component-wise operators, say component-wise multiplication, to come up with the phrase level vector representation. And the intuition here is that you're taking some notion of the average of the meanings of the parts. So with multiplication, it's kind of taking an average in the log space. So how have these models been applied in the recent literature? So they've often been applied in order to learn about similarity judgments. So the goal is to have the model duplicate human judgments of word, phrase, or sentence level similarity. So for example, one very popular task has been that of lexical substitution, where you have a particular target word, say load, and you have some of its synonyms as you can extract from the thesaurus or word net. So you have, say, burn and beat. But it turns out that these synonyms are only appropriate within a specific context. So if you have the face load, then within the context of the face, you can only replace it with the face beam, whereas the face burn would mean something quite different. On the other hand, if you have the fire glowed, you can replace that with the fire burn, but not the fire beam. So far, these models have tended to be applied in tasks in lexical semantics with restricted syntactic contexts. So here it's only in the context of the intransitive subject. Whereas in this talk, I'll explore also applying these methods to, say, a more general notion of inference. And so this is the high-level outline of what that's going to look like. So you start off with some large text collection. You train your compositional distributional semantic model. And first, I'll talk about how to use this in order to acquire structured domain knowledge. And the applications here are in structure induction itself, as well as in automatic multi-document summarization. And then I'll also look at how to evaluate these compositional DS models. And so I'll look at how to evaluate them for their ability to support the kind of natural language inference that I was talking about earlier. All right, so then let's start talking about using distributional semantics for domain modeling. So in other words, this step of the process. All right, so the goal in this part is to have a method for structure induction. So in other words, we want to build some structure representation of a domain. So let me be a little bit more precise about what I mean by that. And I'll use a running example of a legal trial. So first of all, I'll say that you can characterize a domain in terms of its slots. So the participants or entities within that domain. So in a legal trial, you might have, say, the defendant, the jury, or the judge. And you might have, say, the charge or the crime itself. Next, I'll say that we can characterize a domain in terms of the events that happen. So say one event might be the defendant entering a plea. Another might be the conviction or exoneration event. And since this is an unsupervised task, you can think of it as a clustering problem. So it's unsupervised in that there's no manual annotation or labels. And so how can distributional semantics actually help with this clustering problem? So first of all, it can help by providing us with some measure of semantic similarity. So for example, we know that judge and official are semantically similar, then it's more likely that they belong to the same slot. On the other hand, judge and Monday are probably less similar, and so they're more likely to belong to different slots. So in other words, these distributional semantic vector representations let us incorporate some notion of the background semantic knowledge into the clustering process. And second of all, you can also encode other kinds of knowledge into the distributional semantic vectors, including, say, syntactic information. So the model that I'll present that does all of this is called the Distributional Semantic Hidden Markov Model, or DSHMM for short. So this is a model that I presented at ECL last year. So this falls under a class of models called content models, which are basically graphical models that have been applied to learn about domain concepts and structure. And there's been a number of papers on this in the past decade. So one advantage of using a content modeling approach is that there are standard algorithms for the inference and for the unsupervised learning based on the structure of the graphical model. So say EM, Viterbi, inside, outside, and so forth. So let's talk about the structure. Let's describe the structure of DSHMM according to its graphical model structure. So basically, it is a variant of an HMM, which means that it's a sequence model. But whereas in a standard HMM, you have one sequence being, say, a sentence, and each time step in the model being a word, in DSHMM, I'll apply it on entire documents. So here, one sequence is a document, and the time steps are the clauses that make up that document. So here in this example, we have, say, two clauses: the jury convicted the defendant. So these are two clauses within the document, and say there might be a number of clauses in between. And then there will be a number of latent variables to describe the structure of the domain that we're learning or clustering about, and also a number of observed variables for the parts of the text that are being generated. So the first layer of latent variables are these event variables, and so they correspond to clusters that describe the events, as the name suggests. So for example, in the first clause, after training DSHMM, hopefully we'll learn that the cluster here represents the conviction event. Whereas in this teeth clause, hopefully we'll learn that it's some cluster corresponding to the report event. And conditioned upon the value of this latent variable, you generate the actual event head itself. All right, and then the second layer of latent variables will correspond to the slot variables, describing the clusters of entities or participants. So again, after clustering, hopefully you'll learn that this takes a value corresponding to the jury, this to the accused, and to the reporter, and so forth. And likewise, conditioned upon that, you generate the argument heads that you observe. So the novel part about DSHMM is exactly that we also add these vector emissions to the model. So rather than simply generating the word or a lemma token, as in previous approaches, this model also generates the vector representations. And so what ends up happening after training is for the vector emission part, you'll learn some clusters in the distributional semantic vector space. So in this example, we have, say, 2 dimensions, where one portion of it corresponds to, say, the charge or accused event, another to the defendant or accused, and a third to, say, the judge. And all of this is implemented using multivariate Gaussians with regularization. So now let's talk more about the DS part of DSHMM. So that is how we actually come up with the vector emissions themselves. So first of all, so here's where the compositional methods come in. So what happens is that we need to generate vectors for, first of all, the arguments that you see, as well as the events. So for the arguments, what I'll do is I'll actually have the model emit the vector for the argument composed with the argument's head. So in the jury convicted the defendant, you have actually the vector for the jury convicted here. And that's created by using the raw vectors for jury and convict and composing them together. Yeah?
If I can just get clarification of a couple of things, because I'm not positive I'm following correctly. So the diagram you showed on the previous slide, sorry, the one before that,
Okay.
Looked like it might be a dependency parse, except it looks like you were limiting to 2 levels. Is that right? So if the jury had some modifier attached to it, that wouldn't give you a 3rd level.
That's right.
That's
right. Yeah, that's a good way to think about it. So actually, how we come up with this is that we first do a dependency parse of the sentence, and then we pick out the parts of that tree that we're interested in modeling. And so that's how you actually initialize the structure of the model itself.
Okay, but it's always these 3 levels.
Yes, that's right.
And the other question is, when you added in the vectors, I wasn't clear whether those were observed or not. If they're not observed, then I guess they don't help you train the model. So they're just context vectors?
Yeah, so
they're just context words.
There are context vectors that with these compositional operators, which I'll discuss. Yeah.
Okay, so the model is generating the same words twice.
Yeah. So the word lemma itself as well as its vector representation. So
I'm sorry, what I mean is that defendant is generated partly as the word defendant, generated from S12, but it's also being it's also being generated from E1 because it is part of the context vector of E1.
Oh, no. So here it's actually just shown as it is here. So the vector is generated, so the word is generated by S, the condition upon S12, and the vector as well associated with it. And that's it.
So what does it mean to say the context vector?
So the context vector
is,
so basically you can think of it as a dictionary lookup. So I'll talk a little bit more about this, but you have some large external corpus for which you train these vector representations. And then within a particular context, you simply look up in that dictionary, along with these compositional operators, the vector that you see. So this is not clear, maybe we can talk more about it a bit later.
No, it's clear. So these are type lookups, and the corpus excludes the particular sentence you're looking at to avoid
Right, yeah.
Okay, thanks.
Okay, yeah. So thanks for the question. All right. So then we're generating these argument vectors by composing the vector of the arguments with the vector for the heads. And then we also need to have vector representations for the event heads themselves. And to do that, you have the vector for the event head itself, and you compose in the raw vectors for each of its arguments. So what are these compositionality operators? So I drew a number of different compositional ES models from recent literature representing different kinds of information that you can incorporate into the model. So first of all are the simple componentized ones. And also a second method we tried is to incorporate one that is more syntax aware and that it takes into account the particular grammatical role and the selectional preferences of that role. And the third involves actually further training of the word vectors themselves. So rather than have the raw context vectors that have rescaled or whatever, you actually have a separate step of training with using a topic model, LDA. So these are the compositionality operators we tried. And against these, we also compared 2 baseline settings. So the first setting is this no-DS setting, which is to investigate how well the actual architecture of DSHMM works. So this is where we take out all of the vector emissions. And the second setting is to look at the effect of compositionality specifically by having DSHMM with the simple non-compositional distributional semantic method. And so our evaluations are performed on the Text Analytics Conference 2010 dataset, which is a dataset generated by NIST. So it includes a summarization task with it, and it has domain instances from these 5 different domains. So the first task is a slot induction task. So here we want to find entity clusters that are coherent in the human written summaries in this data set. And so an example of a good cluster would be one that's coherent, say judge, official, and Judy, if Judy happens to be named the judge. Or say accused, defendant, and suspect. Whereas a bad cluster would mix together entities of different types, like guilty, mundane, and true. So following standard evaluation protocol of unsupervised methods, we first compute the best possible mapping between the system and gold standard clustering, and then final evaluation measure on that best possible mapping in terms of F1. So let's look at some numerical results. So first of all, here's the result of a previous method by Chambers and Draftsky, which relies on customized similarity measures with agglomerate clustering, compared against the baseline DSHMM method. So what this shows is that even the DSHMM without any distributional semantics outperforms the Chambers and Draftsky model substantially. And so this demonstrates the effectiveness of the architecture of DSHMM itself. And you get a slight improvement if you add in the simple DS model. And then the next set of results. So the syntax method actually doesn't work that much better. Whereas if you look at ProFinder, this is another model I came up with in conjunction with researchers at Microsoft Research. So this is also a content model approach to this task, but it doesn't rely on any distributional semantic information. And it's the best previous result on this task. And if you look at some of the other compositionality operators, it turns out that the component-wise multiplication model works the best. And so these models significantly outperform ProFinder as well. So let's look at what these numbers mean and contextualize them a little bit more by looking at some output. And so I'll show the output of the most likely word emissions associated with some slot clusters in the investigations and trials domain. And I'll show the result of using this DSHMM with the simple vectors, the DS vectors, and DSHMM with the compositional multiplication model. So some clusters are found by both methods. So say the media cluster with report, media, information, conversation, and so forth. But in the simple method, you get these clusters where all of the words are actually semantically related to each other, but it's not really appropriate to put them in the same slot cluster. So for example, you have a case or trial with the prosecutor and judge, and so forth. So this shows that using the DS methods by themselves can lead you astray in that you're clustering things together that you shouldn't be. Whereas with the compositionality operator, this helps to solve this problem because these words tend to compose with different verbs, let's say. And so you're able to better separate, the model is able to better separate out, say, the words related to the charging, as well as the words related to the trial investigators. And this happens again with another mixed cluster. So here you have people being clustered with student, home, and search, whereas in the compositional method, it's able to identify a cluster of the location. So that was the first task in slot induction. So next I'll also show how you can evaluate DSHMM using multi-document summarization. So the goal here is to extract sentences with the important words and topics, and this is learned from the data. So to learn which are the important events and slots, we'll learn this from human written summaries from the same domain. So for example, you might learn that cluster number 3 is important because it represents the conviction event. Do you have a question?
Yeah, so the compositional thing, is what you're saying is that the actual vectors for each word is just you have a dictionary, each word has a distributional semantic, a vector. And then you're saying that given the actual, so when you apply the compositional operators, that means that you look at in the sentence what were the things that actually were happening.
Exactly.
And then you're going to combine
you look at those vectors and combine them.
Okay, so the compositional thing is sentence specific, whereas
whereas the vector training is external.
Okay.
Yeah. Okay. So then, to learn the important words, event heads, and arguments themselves, you learn this from the source text by looking at which are the important or salient words within the particular domain instance. So you might learn that police, shepherd, and murder are important words. Okay, and so evaluation is done using standard summarization evaluation methods with the Rouge 2 method, which compares bigram overlap between the gold standard summaries and the system generated ones. And so on this data set, typical values range from around 4, which is quite poor, to 13, which is human limit. So let's look at some results. So the first result I'll present is that of what's known as the leading baseline of summarization. So first of all, once again, this is a multi-document setting. We have 10 input documents, and we want to generate summaries that are 100 words long. So in the leading baseline, how that works is you look at the most recent document in the cluster, and you extract the leading 100 words from it. And so in news text, this is going to be a non-trivial baseline, because in news text, how news text is often structured is that the beginning of the article is a summary of the rest of the article. So if we compare this against previous content modeling approaches, what we see is that some previous methods, so this is a higher sum, is an influential content model from 5 years ago, does slightly better than the leading baseline, whereas a more recent model by Li et al. Is substantially better, like 1 Rouge point better. So 1 Rouge 2 point is quite important. And then if we look at the performance of DSHMM, so here are the baseline DSHMM methods. So DSHMM without any distributional semantics, and DSHMM with the simple DS models perform basically equivalently to the previous method here. So against these, if you look at some of the compositional operators, the syntax method is substantially better at Rouge 2 of 7.3%. So once again, let's look at some output text. So I won't make you read through an entire 100-word long summary. Instead, I'll present the summary and highlight parts of it. And because this is news text, I have to warn you that the subject matter is not the most uplifting, so brace yourself. All right, so first of all, the summary is able to identify the defendant in the trial. So it's able to show that it's a trial for one of 2 men, and their names are Henderson and the 21-year-old McKinney. And the charges that these men face is that they're charged in the beating death of University of Wyoming student Matthew Shepard. The reason for the trial, Shepard died following a brutal beating near Laramie. The investigators, as well as the potential sentence of they face a death penalty if convicted. So far, all of these aspects were annotated in the data set and expected. But the summary is also able to show that the trial has become a central focus for gay rights activists and others seeking stronger bias crime legislation, and there's no guarantee that these laws will stop hate crimes from happening. So this demonstrates that if you hand annotate everything and rely solely on hand annotation, another potential pitfall is you'll miss something that's actually important, but that you didn't happen to include in your annotation scheme. All right, so far what I've discussed is how to use these compositional DS models in order to improve structured domain knowledge acquisition, as well as automatic summarization. So this is the first time that these compositional DS models have been shown to be useful for a complex NLP application like automatic summarization. So next I'll start talking about the evaluation side of how to evaluate the compositional DS models for their ability to support inference. Okay, so the first question to ask is why evaluate DS models at all? So we've already seen that these compositional DS methods can help improve automatic summarization, and so isn't that enough? So then to answer this, let's go back to this quote by Montague, that the basic aim of semantics is to characterize the notion of a true sentence and of entailment. So in other words, while there's been a revolution in the techniques that's being used in semantics, in that we have lots of great statistical techniques that can help us get better accuracies and generalize better and so forth, that doesn't mean that there's been a revolution in the goals of semantics. So we still really care about inference. And there are also practical reasons to care about this more precise notion of inference, and that more precise inference enables a wider range of applications. So the long-term goal of this program of distributional semantics is to have compositional DS methods that can at once perform the types of inferences that are enabled by logic and semantics, and yet retain all of the advantages of distributional semantics. So for example, being easy to train, having notions of similarity, and so forth. But as I talked about earlier, many existing evaluations don't focus enough on this. So they focus on lexical semantics-based evaluations. So what should an evaluation towards this particular goal look like? So what I'll try to emphasize is that what we care about is meaning rather than structure. So this is basically this idea of argument structured invariance. So now I'll start talking about an evaluation framework we came up with based on this idea of argument structure invariance. So what argument structure invariance says is that semantic representations of sentences should be similar if they contain or express the same semantic relation, regardless of how this relation is actually realized in the text. So first of all, let's think about, so I'll present an example very soon, but for the general idea of invariance, this idea is actually, can be found in other areas of AI. So for example, in vision, you might have an object detector that you want to be able to recognize an object, even if the object is rotated or it is translated. So you want to recognize it as a cat, even if the cat decides to rotate or translate itself. So in language, we don't have two pictures of cats. Instead, we have semantic relations. So here we have a relation of a company, Pfizer, bought another company, Renault Neuroscience. And you can express this particular semantic relation in many different ways. For example, you can put it in the passive voice. So Renault Neuroscience was bought by Pfizer. You can add other kinds of information to it or use a different lexical item. So you have Pfizer paid several $100 million for Renault Neuroscience. And you can even nominalize it so that instead of representing or expressing the relation as a clause, you express it as a noun phrase. Like Pfizer to expand neuroscience research with acquisition of Renault Neuroscience. Yeah?
Do you consider buy and sell to be the same relation?
Yeah, if it's flipped. Yeah. All right, so then our evaluation framework works by basically having this DS model, and we'll pass it some pairs of sentences. So basically all we require of the model is that it gives us similarity scores. So just as a reminder, there's no task-specific training involved, so this is also an unsupervised problem. So we'll pass it two types of pairs. So some of them are high similarity in that they express some common semantic relation, and some of them are low similarity pairs that do not. But in all of our examples, we have pairs of sentences containing the same entity type, so you can't learn something based on the distributional properties of the entity type itself. So a high pair might be, say, Pfizer buys Renault Neuroscience. Pfizer paid $200 million for Renault Neuroscience. And what we want the model to give us is some high similarity score. Whereas a low similarity pair is one that does not share a semantic relation. So Pfizer buys Renault Neuroscience, and Pfizer and Renault Neuroscience discuss partnership. And likewise, we want our model to give us a low similarity score. So basically, the model is evaluated by how well it separates the group of high scores from the group of low scores. So I came up with two tasks that instantiate this evaluation framework. The first is in relation extraction, using a data set by Dinescu and Mooney. So again, because this is unsupervised, the evaluation measure here is this AUC, area under the curve measure. So if you haven't encountered it before, it's simply, the best way to think about it intuitively is that it's the probability that a randomly chosen high pair gets a higher score than a randomly chosen low pair. I also tried a variant of this task, which is a restricted form of question answering. So here we're interested in just argument structure questions because we're targeting argument structure and variance in this evaluation. And the data set here is in the biomedical domain, Virginia and Lewis. And the goal is to predict which sentence in the document contains the answer out of all the sentences in the document. And we do that by comparing the similarity of the question to each of the sentences. So the evaluation measure here is the mean rank of the sentence from 0 to 1, where 1 is the best possible case and that the answer is the most similar. So let's look at the DS models that we evaluate. We've already encountered many of these before in my previous discussion. So the first is the baseline method, which is to just count the number of words that overlap without any DS information. And I'll combine this with methods for DS phrasal models that we've seen before. So for example, you can use the simple vector space model, or the syntax-based selection of preferences model, or the LDA trained model by the Reindeer application. So these methods that I talked about are focused towards building phrase-level representations. And we need a further method to further compose them to the sentence level. And I'll simply use component-wise operators, so component-wise addition and multiplication, which have been shown to often be competitive with more complex methods, even though it's linguistically naive. So let's look at the evaluation results. So on the first task of relation classification, what we see is that the baseline method does quite well already at 0.76, but you can achieve a slight performance gain if you add the compositional DS methods and to statistical significance in these two cases. So while the absolute gain isn't huge, what's important here is that we have some evidence that these methods actually do deserve to be called semantics, and that they really do help us recognize argument structure invariance. And then on the second task, what we see is that the syntax-based method is significantly better than the baseline of the other methods. And so it's likely because in this particular corpus, there are more instances of active-passive alternations. So knowing about the syntax really does matter. So this particular result partially vindicates the work in, say, parsing, in that syntactic information can help us come up with semantic information. But more importantly, we now have an evaluation framework that can let us evaluate many of these other methods that are being proposed recently. So for example, the methods based on using neural networks, or some recent hybrid logic and DS approaches. And so the evaluation code for this evaluation framework is available on my website. So in this talk, I've discussed two major things. So the first major point is that compositional DS methods can help us acquire structured domain knowledge in the form of this DSHML model with an application to automatic summarization, so a complex NLP application. Second of all, I've also talked about how to directly evaluate these compositional DS methods for their ability to support inference by looking at argument structure invariance specifically. So in this particular talk, I focused on my dissertation work on distributional semantics and summarization. So I've worked on a number of other topics, and I'd like to spend just like one slide talking about each of them. So involving opinion summarization, syntax discourse interaction, and semantic knowledge induction. Okay, so first of all, in earlier work on opinion summarization, this is joint work with Giuseppe Caranini at UBC. So I focused on summarizing the user opinions of product. So what you might get on, say, Amazon for, say, a camera or laptop. And the focus here was on looking at the controversiality of the opinions in text. And what we found is that the more controversial the opinions are, the more important it is to express actually the distribution of opinions rather than specific points about each of the aspects of the product, because these might conflict with each other and cause confusion. Next is a project on clear word order language and clear word language parsing. So in this type of language, there are many different possible word orders which convey the same literal meaning. And this actually encompasses a wide range of languages of the world, including, say, German, Russian, Czech, and Japanese. And the freest one of them all is supposed to be Walpuri, which is a language in Australia. So in this example, both of these German sentences, die Frau hat die Mann das Buch gegeben and die Mann hat die Frau das Buch gegeben, correspond to the sentence the woman gave the man the book. So what's interesting here is that despite having a more flexible syntax, we can still use syntactic knowledge to get at the semantics, but it requires, it helps to have a different kind of syntactic analysis. So rather than focusing on grammatical rules like subject and object, you can focus first on the linear order of the constituents within a clause. And so this is known as the topological field structure of German. So my project here was on more accurately coming up with these topological parse trees, as well as applying them to modeling text coherence and natural language generation. And the third project that I'll just briefly mention is on semantic knowledge induction. So in this project, the goal here is to detect a class of semantic operators from text, known as downward entailing operators. And these semantic operators reverse the direction of entailment from a set theoretic point of view. So suppose you have some antecedent P, which entails some consequent Q. In the presence of the negation marker not, this reverses the direction of entailment to not Q entails not Q. But it turns out it's not just the negation marker not that exhibits this property. There's a whole class of words which also have the same effect, including, say, prevent and deny. So detecting this class of words is important for applications in, say, involving entailment, so say recognizing textual entailment and so forth. So it turns out you can actually use distributional information to detect this class of words. And this is by their association with another class of words called negative polarity items. So the most common one in English is any. So these negative polarity items can only occur if there's also a DO in that context. So you can't say I ate any hamburger, but you can say I did not eat any hamburger or I refused to eat any hamburger. And so this connection was first exploited in the CL community by this paper by Dinescu and Gillespie. My work here has been on devising a novel method, a knowledge lean method, using this association, which is able to better learn and discover DOs from text. And so our method is able to increase the number of known DEOs in English by about 75%. And this list of DEOs is also available on the website. Yeah?
Just real quick, what's the motivation for this to be a knowledge lean approach?
So then you can extend this to other languages without requiring extensive knowledge of that language. So you might not, so for example, you don't want to have a parse, necessarily be part of a parse tree or something like that.
So are you saying you want a seed set of NPIs in the new language and then you
yeah, and then
you
just
code
based
train
on that, exactly. So just based on that, decode train that and come up with the system. Yeah. All right, so now I'd like to spend a couple more minutes to talk about some future work where I'd like to take my research next. So in this talk, I focus a lot on the notion of argument structure invariance, which is important at this step where you move from text data to natural language understanding. But after this, you then pass this on to some inference or analysis part of the application. And if you want to provide feedback back to the system user in the form of text, then it becomes important to have the step of natural language generation. So at this step of natural language generation, the question to ask is then, why are there multiple ways to express the same semantic content? So rather than having these alternations be some kind of nuisance that you want to abstract over, and now the question is how to select between them in a particular context. And so we can think of various factors involving, say, coherence and information structure that might be relevant. So I'd be interested in coming up with data-driven approaches that can actually learn this type of decision. So applications of this might be in, say, abstractive summarization, where you want to compose novel summary text, not found in the source. So whereas what I've talked about so far has been on extraction, so concatenating multiple snippets from the source text, in abstraction you compose entirely novel sentences. And the key point here is that abstraction allows us to generalize and synthesize information from many different documents and many different points of different documents. So it's able to potentially automate more of the inferences that make summarization useful in the first place. Another application area is, say, speech generation. So in many of the devices that we use nowadays, say smartphones or Google Glass, they all share in common that a lot of them have very limited screen space. So you will need generation techniques to compress and come up with very short sentences to display, but also to generate sentences which are meant to be, say, spoken back to the user as a form of multimodal application. So a related application is in dialogue systems and in human-robot interaction. So I think it will become important to have online and fluent generation systems so that we can develop robots that we can have coffee with, fall in love with, and then have them refuse to open the door for us. So over a longer term, I'd be interested in more general frameworks for generation. So whereas on the understanding side, we now have a somewhat standardized set of tools, so say we want to tokenize, lematize, part-of-speech tag, or parse and so forth, there's nowhere near the same level of consensus on the generation side. So I'd be interested in coming up with a more general data-driven theory of generation involving factors like the brevity of what you want to generate, the formality of the text, whether you want to perform critical analysis, and how interactive the system is, and so forth. So I think if we're able to accomplish this, then this could lead to much more research in generation and much faster typing of generation systems. So that would be one of the long-term goals. So finally, I'd like to acknowledge my collaborators. So my advisor, Gerald Penn at the University of Toronto, Kwai-Fong Poon and Lucy Vander Wendy at Microsoft Research, and Joseph Vikrani at UBC, as well as funding agencies. So thank you very much. I'd be happy to take any other questions. Yes.
So do you have any sense why it looked like the addition and the multiplication composition operators were behaving differently on the different tasks? It looked like LDA with addition was doing about the same as syntax with multiplication.
So for those results, I showed the better of the two operators. So it's hard to get a sense of why that is. So I think that one issue is how many things are composing. So often it's been found that when you're composing just two words to a phrase level, multiplication works better because multiplication is kind of like taking the intersections between the dimensions and focusing on those particular dimensions that matter. So say, and this is kind of like an implicit form of word census ambiguation. So you have, say, a financial bank or a bank, and if it composes with a particular type of word, those particular dimensions are the only ones that are allowed. But on the other hand, if you're composing a very large sequence of text, then often addition seems to work better, because with multiplication you might be doing too much zeroing out, so that everything becomes zero. So that might be one factor. So I think that is something that merits further investigation. And I also think that in the future, it's clear that these component-wise operators are not linguistically adequate. So for example, they completely ignore word order. And yet they're still able to perform quite well in this task. But I think in the future, the way to go is to come up with models of composition that can actually be more linguistically accurate and also produce better results in these tasks. Yes.
So you talked a little bit about scopal operators, but I think mainly just Edward and Telly environments. Have you thought about discovering other kinds of operators? For example, whether something preserves activity or...
Right. Yeah, so that's actually one future project I'd be really interested in. So for example, one idea I had was on trying to discover, say, adjectives that are non-intersective. So if you have like the former dictator, if you remove former, then it doesn't preserve the entailment relations. So yeah, that's definitely something I'd be interested in. And there's also some work on, say, looking at quantifier-based reasoning with distributional semantics from Italy, from Marco Baroni's group. So I think that's also a very interesting.
So once you've done that, just following up on the quantifier question, how do you do inference from those representations?
So in their work, it's a supervised setting. So they want to generalize entailment relations. So if you know that all dogs entail some dogs, then they want to generalize that to a noun they haven't seen before. So say all cats entail some cats. And so, and likewise, they can try to generalize to different quantifiers. So that's how they perform inference in that. But they have, so far there hasn't been work on looking at above the level of nouns. So that would be the future direction. Yes?
So in the first test that you talked about, which was the category identification for slots and so on, how many elements were being composed together?
Oh, okay. So in the BSHMN model, it's being composed at the local dependency syntactic level.
So are there more than two elements?
Sometimes, yeah. So an event is composed with all of its arguments, which
All
sometimes...
of its arguments.
Yeah.
So actually, you haven't said anything about adjuncts.
About, sorry?
Adjuncts.
Oh, adjuncts. So for this particular model, I did not distinguish, say, complements and adjuncts. So everything
So
that...
adjuncts are also composing.
Yeah.
Okay, so my question was, if instead of having a combination operation, you just generated, let's say, triples of verb and two arguments or whatever, without combining them, but requiring that they be generated together, do you think that the performance would be comparable or not?
So maybe if you have some very sophisticated technique for, say, regularization. Because if you're generating them together, then the state space becomes much larger, and it's much harder to estimate accurate models for that. But it could be possible. Yeah.
So I'm a little surprised that you talk about the argument structure invariance as something to do with inference, because I mean, on a conservative view of things, you have syntactic structure, and argument structure is the center of that. And then you have the logical form, in which all that is thrown away, the first approximation, and inference is done there. So you're looking at the part that you throw away exactly so that you can then do inference.
But the key point is you really need to have that first part solved as a prerequisite for being able to enable.
I agree, but that's syntax, it's not inference.
So it's not inference by itself, but I think it's a really crucial prerequisite for inference.
I'll agree with that.
Yes.
Yeah, so I'm curious how you might handle tense. Tense and mood, actually mood, if you really want to get tricky in this kind of framework.
That's interesting. So I haven't considered those kinds of issues. So I focused on, say, maybe something that you might care about, like information extraction for like raw facts. But that's definitely something that needs to also be handled if you want a general semantic theory. And right now I don't have a clear sense of how distributional semantics can handle that. So of course you can encode it within some vector space, but that's not really distributional. So yeah, I think that would be, that'd be an interesting future research area as well.
Any other questions? All right, so let's thank the speaker again.